Institute. This lesson contains audio narration. Please connect your headphones, or turn on your speakers. Click on the play button to begin the lesson. These are the key objectives that you can expect to achieve after completing this lesson. Describe the principles, techniques and application of the following inspection methods: radiographic and chemical. Click the next. Radiography is the most commonly used non-destructive method to detect subsurface volumetric discontinuities in welds. The radiographic method can be applied to most welded joints but is most commonly applied to butt and corner joints. As with all testing methods, radiography has certain limitations. It is a method that simultaneously measures differences in the thickness and density of the material under examination. There must be enough difference to show up on the film image. It is important that the welding inspector has some knowledge of both methods of radiography used in the inspection of welds: X-radiography, gamma radiography. X-rays and gamma rays both have extremely short wavelengths. This short wavelength radiation contains enough energy to ionize atoms should it strike them directly. It is this characteristic that enables them to penetrate solid objects that would block ordinary light. The two types of radiation affect photographic film in the same manner. Ionizing radiation is dangerous and exposure must be carefully controlled. Radiation cannot be felt, seen, smelled or tasted. Trained, licensed radiographers are responsible for the safety of the public and themselves. Whenever radiography is performed, a safe zone is established and warning signs posted. These barriers must never be crossed unless the radiographer in charge directs you to do so. A typical radiation warning sign is shown. X-rays are generated in an X-ray tube by propelling, at high speeds, a stream of electrons through a vacuum against a target constructed of materials with high atomic numbers and high melting point. Tungsten is a common targeting material. The electron stream interacts with the atomic structure of the target material, temporarily dislodging electrons. Energy is generated from this dislodgement action, 99% of which is heat and 1% of which are X-rays. The heat is dissipated by the copper anode, plus and cooling media in the tube housing. The X-rays are projected in a conical beam from the target material against the weld under examination. The system is electrical and no ionizing radiation is generated or retained in the system when it is switched off. In addition, the wavelength is adjustable through changes in the voltage applied across the tube, which allows adjustment of penetrating power to suit material type and thickness. The density of the electron stream is controlled by the amount of current or milliamperes applied to the tube. Wavelength is controlled by voltage input across the tube. Higher voltage produces shorter wavelength, which gives the X-rays more penetrating power. X-ray machines are available in different sizes to suit the needed penetrating power. The figure shows a 300 kV X-ray tube and control panel. It is capable of producing images through steel weldments of up to 75 mm, or 3 inches. For greater thickness material, more voltage is needed. The figure shows a 4 MeV X-ray machine capable of penetrating up to 300 mm or 12 inches. A safe room is usually built for large fixed X-ray installations. The equipment is cumbersome and somewhat delicate, even the units designed for portability are relatively heavy and awkward to maneuver. Gamma rays used in radiography emanate from a radioisotope commonly called a source. A source is a small piece of radioactive matter of a size that emits a known amount of radiation. The wavelengths of the gamma rays are fixed by the type of isotope, cobalt-60 or iridium-192, which emits them. Cobalt-60 has wavelengths that are much shorter than iridium-192 and therefore have more penetrating ability and are used to inspect thicker materials. The sources of radiation are constantly emitting ionizing radiation and cannot be shut off. The sources therefore are shielded in a protective casing manufactured from extremely dense materials such as lead or tungsten. The material absorbs the radiation and protects the operator from exposure. When the source is to be used, it is remotely handled. A drive cable is connected to the source pigtail and projected through a hose called a nose tube to a position from which the radiation passes through the object and onto a film. The drive cable is long enough to allow the radiographer to stay a safe distance away from the source while it is out of the shielded position. The figure shows a typical setup for gamma radiography. The source is cranked out of the safe position and is deployed through the nose tube to a position inside the tubular weldment. The source remains in position for a period of time calculated to produce the best image on the film. The figure shows a gamma radiography setup. As X-rays or gamma radiation are directed at the weld, a certain amount will be absorbed by the structure of the metal and the remainder will pass through onto a film that is placed into position. The amount of radiation absorption depends upon the material type and thickness. Each material, steel, aluminum, copper, and so forth, has a different density. When a weld has internal discontinuities such as slag or porosity, more radiation will reach the film under these areas than in adjacent areas, which have no discontinuities and are therefore able to block more radiation. In this manner, different amounts of radiation reach the film. These differences in the amount of radiation passing through the weld appear on the developed film as light or dark shadows. These differences are called changes in film density. The radiographic film is interpreted by evaluating the shape, density and location of the images created by slag, porosity, or other discontinuities. When a discontinuity in a weld does not constitute a relatively substantial difference in the total cross-section of the weld, the difference in radiation absorption can be less than detectable by the density difference it creates. That is, the image on the film will not be pronounced. Certain flaws such as tight cracks, overlap, incomplete fusion, and so on, can present so little difference in the amount of radiation absorbed that no discernible image will appear on the film. Where the beam of radiation is not directed into the plane of the defect can be completely missed. This is the main limitation of radiography. In general, radiographs made with X-rays are superior to those made with gamma rays mainly due to the fact that radiation emitted from X-ray equipment can be adjusted in penetrating power. In steel up to 50 mm, this fact is demonstrated by superior radiographic sensitivity and clarity of the defect image. Above 50 mm, the wavelengths necessary to penetrate the steel are of the same order of magnitude to those of gamma radiation, so that radiographic sensitivity is reduced somewhat. Construction codes such as ASME Boiler and Pressure Vessel Code, Section 8, CSA Standard W59 and AWSD 1.1, dictate that the way in which a radiograph is produced will meet specific requirements. One of these requirements, which is important to a welding inspector, is the use of a device known as a penetrometer, or image quality indicator. The penetrometer is placed on the parent material adjacent to the area of the weld that is to be radiographed, usually on the side of the material that is closest to the source of radiation as shown. The image of a discontinuity is affected by the radiographic technique. The geometric setup of the source in relation to the object being examined directly and the film affects the image created on the film. Reducing the source to film distance, d, increases the image distortion, penumbra. Penetrometers serve to preclude this possibility because the image must be clear enough to enable the interpreter to see the outline and the qualifying holes. The figure shows the placement of the penetrometer according to the ASME Boiler and Pressure Vessel Code. The figures indicate the placement of image quality indicator in accordance with CSA W59 requirements. There are different types of penetrometers. Some have wires of different diameters, others have holes or slots of specific dimensions machined into them. Examples of hole and wire type penetrometers are shown in the figure. In general, Construction standards will dictate that a penetrometer thickness shall be 2% of the thickness of the material to be radiographed. The penetrometer, therefore, is used to assess the quality of the radiographic technique and the quality of the film image. The penetrometer is an object of known shape, size and geometric features. Seeing certain aspects of the image of the penetrometer gives the viewer a sense of how clearly the image of a discontinuity would appear. The smaller the hole or wire visible in the radiograph, the better the resolution or ability to see defects in the radiograph. The thickness of the hole-type penetrometer shall not be more than 2% of the thickness of the plate. In each penetrometer there shall be 3 holes of diameter equal to 1, 2 and 4 times the penetrometer thickness, but in no case less than 0.010 inches. Wire-type penetrometers have wire sizes ranging from 0.08 mm, 0.0032 inches, to 8 mm, 0.32 inches. Each penetrometer has 6 different wire sizes in it. Tables in the codes indicate which of the holes or wires must appear as images on the radiographs. Each penetrometer has numbers affixed to it identifying the material and minimum thickness of the plate. Standards of acceptability for welds subject to radiographic examination have been established by various code committees and are detailed in codes and standards such as ASME Sections 1, 3 and 8, API 650, CSA Standard W59, ANSI 31.1, etc. When the radiographic report specifies that indications of discontinuities are unacceptable, the defective area of the weld is removed and the cavity re-welded. The repair is then radiographed in accordance with the original procedure. Radiography is the most successful and reliable method for non-destructive testing of welds. There are limitations to the test method, some of which have been pointed out. Where the limits of the method have been defined, it is probable that an alternative test, such as ultrasonic, will serve to complement radiography. Electronic systems are available for chemical analysis of metals. They are reasonably compact and portable and give essentially instant results. The major limitation of many older instruments was the inability to analyze for carbon content. Many of the newer instruments are capable of measuring carbon, sulfur and other trace elements. Now that we have reviewed the material, let's see what you remember. Click the play button to check. You have completed this lesson. You are now able to describe the principles, techniques and application of the following inspection methods: radiographic and chemical. Congratulations! You have completed this lesson. Click the replay button to begin this lesson again, or click